universe.
Yes, thank you very much. Let me just start sharing my screen. There we go. Okay, I think everything is set up, right?
Yes, very good.
Okay, let me start. So first of all, I'd like to thank the organizers for still kind of going on with this conference and giving me and the other speakers the opportunity to speak. It's of course very bizarre times at the moment, but I think it's great to see that still physics is continuing at like full force and everybody's still being able to have this nice conference. So having said that, what I would like to talk about today is the sitter space. So this is based on some work I did together with Gary Shu, which came out in February, and also some work in progress that I'm currently doing, also together with Gary, Alex Cole, Edward Morvan, and Jan-Peter van der Schaar. And what we realized while we were kind of doing this project is actually the thing that we were describing was a love story in the sitter space. And the two main players that play the important role in this love story are two observers that go by the name of Alice and Bob. So Alice and Bob, they are two observers living in the sitter space, and they both are sitting in their static patch, and they're surrounded by a cosmological horizon. So they were happy together. So as you can see here, their kind of Hubble patch overlaps. But one day something terrible happened, and they decided to separate. So they decided to separate, and after some time had elapsed, their respective Hubble patches was no longer overlapping, and they were truly separated from each other. So kind of written in terms of a Penrose diagram, let's say that Bob stays behind here at the south pole of the sitter space, and that Alice was leaving through the horizon, and they were separated causally from each other. However, quickly after they separated, they both very much regretted their decision, and they wanted to return to each other. So, for example, what could happen is that Alice decides to turn around. However, because there's a cosmological horizon separating them, it still seems futile for them to rejoin and being able to enjoy the rest of their lives together. So the question that we would like to answer is, are there things that Bob can do such that Alice and Bob can rejoin together? Or kind of set in a more formally correct way is, if you are living in a de Sitter universe and you throw, let's say, a qubit of information through the horizon, can you retrieve it from your horizon? So you might wonder, okay, this is a very interesting love story, but why is this relevant for physics? Well, we know that similar types of thought experiments involving black holes, they typically learn us a great deal. So for example, if you think about evaporating black holes, and we throw, let's say, a qubit of information through the black hole horizon, and we wait a bit such that the black hole starts emitting Hawking radiation, then we know that if we kind of naively apply effective field theory, that we can run into an information paradox. Or a different type of paradox, if you believe that somehow the information will come outside of the black hole, and then after you have recovered it, what you can do is you can take this qubit of information that you have, and you decide to also jump into the black hole. And then naively, you might come to the conclusion that what happens is that you observe the same qubit twice. So this would be in violation of the quantum no-cloning theorem. So in essence, what these type of thought experiments tell us is they tell us about the validity of effective field theory inside gravitational systems. So that's very much in the spirit of the swampland. And what is nice about black holes is that by now we have developed some tools to kind of understand these paradoxes and how they are resolved. But the status in the sitter space is much less clear. But it might be very relevant also, because if you think about inflation or dark energy, that's a phase that is very closely approximated by the sitter phase. So more generally, the question we would like to answer is, can we use kind of the tools of quantum information in the same way that they have been applied to black holes? Can we use that to put some bounds on the sitter space? So the rough outline of my talk will look as follows. So first I will talk about information recovery in black holes. So this part will be mostly review. I would just want to get everybody on the same page. And then we'll move on to the sitter space. And then there are some key ingredients that will be important. So in particular, two key ingredients are shockwaves in the Zillow space and information scrambling. So we'll talk about that. And then we'll actually use some of these tools to talk about information recovery in the Zillow space. And we'll see how these kind of information tools, how they could possibly apply to the Zillow space and how they put bounds on the Zillow space. So this last part, the possible Vino consequences, that will be slightly more speculative, but I thought it was still very interesting to mention. So let us dive right in and talk about information recovery in black holes. So when we talk about black hole information, the picture that we have in mind is that, let's say we have some evaporating black hole here, and we have Alice here who decides to jump inside of the black hole, or that she throws like a qubit of information inside of the black hole. Then we know via Hawking evaporation that this black hole will start emitting radiation, which will be approximately described by a thermal density matrix. And if Bob wants to kind of recover Alice or recover the information that Alice threw in, then he has to start collecting this radiation. And then an interesting question that you could ask yourself is, how long does Bob have to wait? Or how much radiation does he need to collect before he can recover the information that was thrown inside of the black hole? And kind of the first or the answer to this question was given by Page in a very famous and by now old paper. So what Page did is he calculated the entanglement entropy associated with this radiation. And he assumed that the black hole initially starts out in a pure state. So then what he found is that if you then compute the entanglement entropy of the radiation, is that it will initially increase. But at some point, because the black hole is only described by a finite amount of states, so it only has a finite entropy and hence a finite Hilbert space, then at some point, that entanglement entropy should start to go down again. This is precisely the moment when the entanglement entropy starts to go down again, that it becomes possible for Bob to recover the information. So Page calculated exactly the time scale where this turnover takes place, and he found that it was given by the following time scale. So this is by now, this is known as the Page time. So you might notice that for a large black hole with a large entropy, this time scale is very, very long. So Bob needs to collect a huge amount of radiation until he can recover, let's say, a bit of information from the black hole. However, this was not the end of the story. So what was later realized in a paper by Hayden and Pascal is they did something clever. And that is, they said, well, let's say that Bob first waits a while. That Alice waits a while. So Bob first starts collecting radiation until he reached the Page time, and only then you throw in a new qubit of information. So then you're already around this point. So what then happens is that if you throw in some new information, is that information will come out as fast as possible. And the time scale that it will come out is known as the scrambling time. So you see that the scrambling time is a much shorter time scale because it scales logarithmically with the entropy of the black hole. So what this means is that so that first what you have to do if you throw in this new qubit of information through the black hole, then this qubit first has to be absorbed before it can be re-emitted. And kind of this absorption time scale, that is given exactly by the scrambling time. So in the Hayden-Pascal paper, they gave kind of a sort of order of magnitude type of estimate for the scrambling time, but you can actually compute it more precisely by making use of the so-called thermal field double state. So the thermal field double state is not described just a single black hole, and it actually describes a double-sided black hole. And it describes two black holes that are actually maximally entangled. So that is given by the following state here. So here NR and NL are the energy eigenstates of kind of the right system here and the left system here respectively. Then you have this factor here, this kind of thermal factor which maximally entangles them. So what this means is, let's say you trace out the right part, or sorry, the left part of this diagram. What this means is that you're left with a thermal density matrix. So this describes a black hole that is in thermal equilibrium. What you can do is you can calculate the time scale it takes for the black hole to absorb this qubit by perturbing this thermal field double state. And the precise way you do this is by computing a so-called out-of-time ordered correlator. So what this means is that you're looking at, let's say, a perturbation W to this black hole, and then you see if you have some other operator V0, how that reacts to the perturbation. So then by computing the overlap where you switch W and V, that is when you get the out-of-time ordered correlator, and it basically measures the sensitivity of initial conditions of the black hole. So if you compute this out-of-time ordered correlator in this black hole background, what you find is that initially at t equals 0, it starts out at 1, but then it starts to decrease exponentially fast. So what this means is that this black hole is exponentially sensitive to a slight change in initial conditions. And the time scale where this correlation function decays to 0, that is precisely known as the scrambling time, and gives you the time scale when a qubit has been absorbed by the horizon. And what is kind of interesting about black holes is that they are known as fast scramblers, which means that the scrambling time is as fast as theoretically possible under some reasonable assumptions. So this is the kind of more technical way how we see that black holes still take a scrambling time before you can get information out of them. And what's actually nice about the thermal field double state is that you can kind of model the recovery of information from a black hole by this thermal field double state. That works in the following way. So it was very nicely explained in this paper by Maldacena, Stanford, and Yang. So the situation that we have in mind is the following. Let's say there is some black hole, it is evaporating, and Bob starts collecting the radiation. Then after a sufficiently long time has elapsed, Bob has a large amount of radiation. What he does is he collapses this to a second black hole. But because this radiation was maximally entangled with the first black hole, you now have created approximately the thermal field double state. Then, after the thermal field double state has been created, Alice decides to throw in some information inside of the black hole. And then the idea of recovering information successfully from the black hole can be rephrased as the question of successful information exchange between the two boundaries of the thermal field double state. So what this does for you is this gives you a gravitational bulk interpretation of information recovery. And this will be a point that it will be crucial in the Sitter space, where, for example, we don't have a nice non-gravitational holographic dual. We just have a gravitational de Sitter space. So in that sense, it will be very useful to consider such a picture there. So more precisely how this information exchange works is as follows. So in these papers by Gauge, Veres and Wall and Maldacena, Stanford and Yang, they realize that if you take a thermal field double state, is that you have to, when you have to exchange information from the left boundary to the right boundary, for example, then normally this is not possible because these two regions are causally disconnected. But what Bob can do is he can apply a perturbation that couples the right boundary to the left boundary by moving in the ambient space. And then if he chooses the sign of this coupling in a very precise way, then what you find is that kind of the bulk dual of this is a gravitational shockwave injected at t equals 0 on both sides, which importantly has a negative null energy. So by allowing for this negative null energy, what happens if you have a geodesic that is crossing these shockwaves, it will experience a slight time advance, but in such a way that you can now send some information from the left boundary to the right boundary and vice versa. So now it becomes possible when Alice throws in some information inside the first black hole for it to escape to Bob. Then kind of Bob applying this shockwave protocol is a gravitational interpretation of the Hagen-Pascal decoding protocol. So this will be the kind of key idea that will be used in the Sitter space, and we will see some important differences also with the black hole case. Okay, so now that I have reviewed the black hole case, let us move on to the Sitter space. So kind of the important thing that you should keep in mind is that the scrambling time for black holes played a very important role. And we'll see what role it plays in the Sitter space. So first, the analog of the thermal field double state in the Sitter space is the so-called Bunch-Davies vacuum. So what a Bunch-Davies vacuum does for you is if you take two static observers, let's say one that is living at the South Pole and one that is living at the North Pole of the Sitter space, then the Bunch-Davies vacuum maximally entangles these two static patches of these observers in a very similar way as was happening for the black hole case. However, a sort of difference with the black hole Bunch-Davies, or sorry, with the black hole thermal field double state, is that the Bunch-Davies vacuum is an attractor. So what this means is that if you perturb the thermal field double state in the Sitter space slightly, then typically what happens is that these perturbations redshift away. You will kind of fall back through the Boyne-Davies vacuum again. So that is slightly different for black holes, where the thermal field double state is actually unstable. So now, similar to what we did for the black hole case, is we like to understand how fast information is absorbed by the de Sitter horizon if we throw a qubit through the horizon. So, said more precisely, what we need to do is we need to compute this out-of-time ordered correlation function in the Sitter space. And just for black holes, the thermal field double state written down here looks very similar. You have a right region, a left region, then you have kind of this thermal vector that maximally entangles it. Okay. But before we can compute this out-of-time ordered correlation function, we first need to know the behavior of shock waves in the Sitter space. And the way you can derive that is by considering, let's say, a particle in the Sitter space and then give it an infinite boost. So that will create a shock wave for you. So for kind of convenience, we will just focus on three-dimensional de Sitter space, in which this becomes a very simple solution. And it will be useful to introduce global light cone coordinates. So you have a u coordinate and a v coordinate, which are indicated here in the Penrose diagram. And then when you take this structural de Sitter solution and you give it an infinite boost, what you find is that you create a shock wave geometry, where in the metric, the effect of the shock wave is given by this term that is proportional to dv squared. So you see that here there is a delta function that peaks at v equals 0. So that means that this geometry describes a shock wave that is localized along the past horizon at v equals 0. And this parameter alpha, it shows up in the stress energy tensor, and it measures the energy of the shock wave. And importantly, if you impose the null energy condition on the stress tensor, then you find that alpha has to be bigger or equal than 0. But what this means is that, contrary to the black hole case, is that if you have a positive energy shockwave in the Sitter space, that already when you have a geodesic that is crossing the shockwave, it will experience a time advance. So this is different from the black hole case. And kind of the intuitive reason for this is that by having some positive energy in the Sitter space, you're sort of slowing down the expansion, and becomes easier for an observer at the North Pole to reach an observer at the South Pole and vice versa. You can also show this in kind of a more rigorous mathematical sense, and this was done in a paper by Gao and Wald in 2000. Okay, so how does this relate to computing this out-of-time ordered correlator? So scrambling is, in a sense, Bob knowing that Alice has truly left, and that he has to do something about it. So this is when something has scrambled over the horizon. When this out-of-time ordered correlation function goes to 0, that is actually when Bob knows that Alice has left. So what we can do to compute the out-of-time ordered correlation function is we can follow some of the results of the paper by Schenker and Stanford, where they computed out-of-time ordered correlation functions for black holes. And the way you can describe it is basically by an overlap of in and out states. So we have here a state that is created by inserting an operator W on the left and an operator V on the right, given by blue and red. And these can travel along these lines here. And you can compute the overlap at a state that is created by the same operators, but now here indicated here in the diagram. And then the out-of-time ordered correlation function, as I said, is just given by the overlap. And in the Schenker and Stanford paper, they give a precise derivation for this overlap. Because it's not very enlightening to show it to you, I decided not to display it. But you can look in our paper, or otherwise you can ask about it later if you're interested. So when you do the computation, you find that you can write down the expression for the out-of-time ordered correlation function. But typically, it seems very difficult to solve it completely analytically. So what we did is we just focused on conformally coupled fields for which the ingredients become much more simpler. And then you can solve the out-of-time ordered correlation function analytically. So that gives a result in terms of special functions. And by expanding those, then you finally find the out-of-time ordered correlation function, which looks as follows. So the important thing to notice here is that indeed, just as for the black hole case, it starts out in 1, and then there's an exponential decay. So if you compute the time scale where this correlation function dies down to 0, you find that this is the scrambling time, but then in the Sitter space. And interestingly, just as for the black hole case, the black holes act as fast scramblers. The Sitter space also seems to do that. So for the black hole case, you had a factor of beta over 2 pi times the log of the entropy. So when you fill in the Hawking temperature of the horizon, then that you find this expression. Okay, so what does this imply for the recovery time? So from Hayden-Preskel, this suggests that it should be possible to recover information already after scrambling time. So let's see how that works. So for that, we also need to think about the kind of traversable wormholes, but then in de Sitter space. And as I already mentioned, a nice feature about de Sitter space is that you just need positive energy to create kind of a traversable wormhole that connects the opposite poles of de Sitter space. So if you have, let's say, a shockwave with positive energy that is symmetric at t equals 0, and you look at geodesic inserted at the time t gamma, then that geodesic will experience a time advance. And the statement that information has been successfully exchanged between the two poles means that the phi coordinate here should be shifted negatively. So that is when the wormhole is traversable, that is when phi is shifted negatively. So we need to relate it to the parameter alpha. But as I said before, alpha is related to the shockwave energy. So here it's proportional to the de Sitter length, the Planck length, and the energy of the shockwave. However, to actually create the shockwave, what Bob needs to do in de Sitter space, he needs to start collecting some energy and form that into a shockwave. But typically, Bob only has access to modes that are of the order of the Hawking temperature. So that means that there are modes that have an energy of the order of 1 over the de Sitter length. So when you combine these ingredients, what this means is that the time difference between the shockwave t equals 0 and the time that Alice left, t gamma, should be given by the following relationship. So it should be given by the scrambling time. So indeed, we see here that there should be a time difference between leaving and retrieving of a scrambling time, also in de Sitter space, in order for information recovery to be successful. But of course, this was kind of a situation where we have a two-sided de Sitter space. But in kind of the scenario I sketched in the beginning, we are just talking about the single-sided de Sitter region. So we should also talk about that. So to talk about the single-sided region, it will still be convenient to use the global picture, but then we can, in principle, describe everything from a single-sided perspective. So now what has to happen is that Alice really needs to regret her decision to leave from Bob's static patch. So there needs to be a point where she turns around here. So there will be some reflection time. Then if everything works out nicely, then she will be shifted positively, she will be shifted negatively along this direction. So there will be a time advance, and then she can reach back to Bob at the South Pole. So again, the shift of the that Alice experiences in the shockwave will be given by the energy of the shockwave. And before, so the time that it takes for Alice to leave and Bob to apply his shockwave, let's say that it takes n gamma e-volts. Then that means that the total energy of the shockwave or the shift alpha will be proportional to this n gamma. And again, we want Alice to make it back to the South Pole. So that means that now the u coordinates should be shifted negatively. And then finally, what you can do is, if that all happens, then you can calculate the time it takes for Alice to actually return to Bob. And that will then be given by the time it takes for Bob to collect all the radiation and send a shockwave, plus the time it takes then after Alice has crossed for her to return to Bob. And then you will find the following expression. But then let's say also that Bob is kind of smart and he wants to be sort of lazy and collect as less amount of information as possible. Then he can extremize over the time it takes to collect the information. And then what you find is that the total time it takes for Alice to leave and return is again given by the scrambling time. So this seems all very consistent with kind of the Hayden-Preskel idea that it should take a scrambling time for you to recover some information after you have thrown it through the horizon. So that also seems to work for the de Sitter space, which is very nice. Okay, so we learned that it seems that by doing the shockwave protocol, it is possible to recover information in the de Sitter space rather fast. So you might wonder, what are the phenomenological consequences of this? So this will be slightly more speculative, so we haven't worked out all the full details, but I would like still to sketch a bit of some of the possible consequences that could have. So it's already clear from the beginning, both from black holes and from the de Sitter space, that because both systems have a finite entropy, there should be a bound on the amount of information that you can send through the wormhole. And that's basically just because there's a finite amount of states that are at your disposal. So this was actually calculated, I think, already in the original traversable wormhole papers for black holes, but it was kind of nicely elaborated upon in this paper. So there are a few kind of conditions that you would like to satisfy when you send information. And one of the things that you would like to avoid is basically that by inserting a shockwave inside the Sitter space, is that you backreact so strongly that you destroy the space-time. So you basically don't want to create black holes. So this condition can be translated into a bound of the energy of the shockwave. And then if you translate that to a bound on the shift that you experience, it bounds the shift to be at most of a de Sitter length. And similarly, you also like to avoid that the message that you send through the wormhole will backreact too strongly. So you also want to make sure that so the energy of the message is given by the total number of bits that you send times the energy of a single bit. That should similarly be bounded by the Planck scale. And finally, you also want to make sure that the message that you send to the wormhole actually makes it through. So you want to make sure that its quantum wavelength is small enough to fit through the wormhole. So this translates to the statement that the energy of a bit should be bigger than 1 over alpha. So combining these three bounds, what you then find is that the maximum number of bits of information that you can send through the wormhole is bounded by the entropy. So this is kind of a very natural bound, and it's very similar to what happens for black holes. Okay, so what does that imply? So now you can imagine a situation where in the Sitter space that there is some expansion going on. Bob is at the south pole of the Sitter space, Alice is living at the north pole. And let's say that Bob wants to update Alice about the local expansion rate that he is experiencing. So what he will do is he will send kind of 1 bit of information per e-volt to Alice. So this, in a very schematic way, this is sort of similar to inflation, where there are modes being stretched to the horizon, and typically there's like a single mode per e-volt that is created. And then we know from our previous argument that the total number of bits that Bob can send to Alice should be bounded by the de Sitter entropy. But what this means is that semi-classical de Sitter space can only be supported for n smaller than s de Sitter of e-volts. Because we just calculated that if you would send more information, backreaction would become very strong. And this is sort of intriguing because it's similar to bounds that have been derived on slower inflations from slightly different arguments. But of course, this all depends in the scenario that we are considering about exactly how fast information is being sent. So for example, if you would send all the information at once, then you would only be able to have not take backreaction into account for a scrambling time, because that is the time scale it takes for information to be recovered. So we're still kind of working out if you can actually use some of these arguments to come up with a slightly sharper argument and a sharper bound. So that brings me to the conclusions. So what we did is we studied information scrambling and retrieval in the Sitter space, first by starting with black holes, and then applying some of these lessons to the Sitter space. One of the key things that we learned is by computing an out-of-time ordered correlation function, is we learned that the Sitter space is a fast scrambler. I should mention this was originally already conjectured by Susskind in an older paper, but the result with Gary was the first time where the out-of-time ordered correlation function was computed rigorously for the Sitter space. And as a consequence, Bob and Alice can rejoin, and information can be recovered in the Sitter space, which means that they can return to each other, which is of course a good thing. And by applying bounds on information transfer, we found a kind of speculative bound that maybe could lead to a bound on the number of e-volts that is possible for the Sitter space to be sustained in a semi-classical manner. So thank you very much.
Okay, well, thank you very much, Lars. It's a very interesting talk. And yes, you may consider sending your story to Hollywood. Maybe it may work. Anyway, so I can see Miguel Montero is raising the hand. Is that true, Miguel?
Yeah, that's right. Yeah, okay. Yeah. Thanks for the talk, Lars. I really like the story. So I have a couple of questions. So why do you take the energy? You at some point you said that the energy that the observer in one static path has access to is bounded by the Hubble scale, or that the total mass of the meshes has to be lower than m Planck. But I would imagine that it's just the energy density that has to be bounded by m Planck, right? like for instance, you just take I don't know, like you take this pen has more mass than M Planck and lives in the center, and I can, right?
Mm-hmm. Yeah, so there were two boundaries. Let me go back to this slide. So the first bound, the fact that typically what happens for this bound on that we want the basically the energy of the message that we're sending to be bigger than the Hubble scale. So that's basically a consequence of the fact. So when you calculate the proper time that the wormhole is open, so from in the frame of the shockwave, what happens is that it's only open for a very short time. So that means that if you now compute the time when you send a message through the wormhole, that if it will be if the energy will be smaller than a Hubble radius, it will mean that you will kind of miss the wormhole. So because of the quantum wavelength, it will not fit through the wormhole. So that's why you need to bound that.
But that it can be bigger than it, right? It can be bigger than that.
Sorry?
It can be bigger than that because that's shorter
Yeah,
wave.
yeah, exactly.
Okay.
Exactly. So indeed,
Okay, good. Yeah, I got it backwards then. Yeah. So also, like, since you have this picture, just for this, for the protocol to work, you need to have the shock wave incoming from the North Pole as well, right? So there has to, right?
So you mean that there's like this symmetric shock wave?
Yeah, or at least you need the north part, right? So I'm not sure. I'm not sure actually if you need the south part, right, to reflect the. Maybe you do, but. Right? So you need both. That's what I'm asking. Do you need both, or could you do it with just one side? Could just be both sending in a shock wave, or do you also need like Charlie on the North Pole?
So yeah, very good. So in principle, if you just really do a purely single-sided perspective, you could just have one shock wave, because then you have one shock wave, and then Alice turns around here. So the reason why we kind of consider this symmetric shock wave, that if you really look at the global state of the thermal field double state, then the Hamiltonian constraint requires that basically the left Hamiltonian minus the right Hamiltonian is 0. So then that means that you will also need to introduce some energy at the other pole. So that is sort of similar. If you take a Schwarzschild de Sitter solution, then you will find that it will describe some energy at one pole. And if you maximally extend that space-time, then you'll find some energy at the other pole also. But in principle, if you're just interested in a single-sided perspective, you could just focus on one region.
That's kind of like if you go to your plot in the one-sided thing, you have like the matter that's coming out of the horizon. It's coming before I send in the shock wave, right? So it seems a little bit Okosa, right? Like first the matter comes out, like the blue line comes out.
No, so this is.
Oh no, that's the matter coming. That's right.
Yeah, so this is Alice leaving. Then she hits the shock wave and then she returns.
Very good. Okay, thanks.
Okay, more questions? I don't. Oh, is David Andrew?
Yes, thanks. Yeah, thanks for the nice talk, Lars. So all these bounds that you showed really are reminiscent of this TCC, and I think we discussed about it. But can you comment on this just from your slides, or?
Yeah, sure. That's good. So indeed, so the TCC seems very closely related to this. So in that case, so the statement of the TCC is phrased in a different way, but up to like a factor of 2, it's given by the scrambling time. So for example, here this scrambling time given here. So in the TCC, I think so this is in 3 dimensions. So let's say you would write this in 4 dimensions. So then it would be roughly speaking L log m Planck squared over h squared. And you could bring down a factor of 2 from the log. And the TCC is half of that. So it's just given by an L log m Planck over h. So from what we didn't really directly see any pathology after the scrambling time. But the only way how you could, I think, in this picture, see something that would go wrong if inflation, for example, lasts longer than a scrambling time, is in this back reaction bound. So here we kind of just considered the sort of minimal situation, where if there's 1 bit of information sent per e-fold, then this bounds inflation to be less shorter than S de Sitter e-folds. But then if you, let's say you would try to send all the information at once, then that would mean that you find that the number of e-folds is bounded by the scrambling time. So that is the TCC bound after a factor of 2. But I think from this perspective, it's not really clear why that should be the precise bound. So that's something we're also still thinking about.
Actually, that was going to be my question. So do you have an argument for is there something special to send one bit per e-fold?
It's kind of the slowest rate, and it's in a very sketchy manner. It's similar to inflation, where you create like one. Roughly speaking, there's one mode being stretched to the horizon per e-fold. But this is pure de Sitter space, so I don't think we can directly apply this to inflation.
Okay, very good. Are there more questions? I don't see. So Jim has an announcement to make before we finish. And so, but before that, let's all thank all the speakers today. It was very good.
So I think Miguel has another question. I can't tell.
Yeah,
sorry.
Sorry, a quick one.
Go ahead. Yes.
Yeah. So I guess that when in the last slide where Bob starts throwing information to let Alice know about how this thing is increasing, he must be taking the qubits from somewhere. So if he has a lot of qubits in some region, he has a black hole, and if you have a big black hole, that also shrinks the horizon. So does that affect the picture?
Yeah, exactly. I think that's kind of a sort of complementary way of seeing it. It's just kind of, so I had one kind of backup slide, which was that Bob is actually fooling himself, because what's happening at the moment that he starts collecting some information, the horizon shrinks a bit, but then when he releases it, it increases again. So from that perspective, when Alice turns around, she will be outside of kind of Bob's new horizon. But then if he would not have collected the matter, the moment where she turns around will be still inside of the old static patch.
I understand.
So it's kind of the consequence that in the de Sitter space, really everything back reacts. So yeah.
That's very nice, thanks.
Very good. Okay, so now I think that's all again. So thank you very much, Lars. It was very good. And so Jim, do you have an announcement?
Yes.